Hi everybody, welcome back. In the last video we introduced concepts involving mechanical energy and we motivated a conservation of energy idea. So we're going to further explore conservation of energy in this video. So the law of conservation of energy really says, long story short, the total energy in a closed system just before something happens is the same as what it is just after something happens. This is important because energy changes forms, and a lot of times it's easier to measure one form than another form. So if you know what the total energy was before something happened, and you're able to measure one of the forms after it, then you're going to be able to make a prediction of what some missing quantity might be. So let's take a look at how this is going to go. Now, first we are going to make the assumption that there is no work done on or by the system. In other words, no energy enters the system, no energy leaves the system. So no friction, no rockets, or anything like that. So let's consider a cyclist going at a pretty decent clip on a bicycle, 10 meters per second. That's like 23 miles an hour. And the question is, if the cyclist is coasting, how high up the hill will he go with the bicycle before turning around? In other words, not pedaling, but just coasting. What's the maximum height? So first we're going to assume that no energy enters or leaves the system, which means that no work is done on or by the system. So no motors, no rockets, no pedaling, no braking, no friction, etc. So in other words, this is a perfect world type of scenario. What we're going to do is we're going to label two locations, the bottom of the hill and the top of the hill. And we're going to write down everything we know at each of those locations. So first of all, at the bottom of the hill, we know that the rider has a speed of 10 meters per second. And we know that the top of the hill, that's what the maximum height is. Now, we also know something else. Since it's the maximum height, we know that the velocity at the top of the hill is 0. If it wasn't 0, then he would keep going, which means it wouldn't be the maximum height anymore, or he would be already going in the negative direction, which means the maximum height was actually reached somewhere previously and it was higher than we thought it was. So by definition, the maximum height is the turning point. So that is an implied given. Now, total energy has lots of different symbols. Sometimes you'll see it written as capital E. A lot of times it's going to be sum over E, that capital Greek letter sigma indicating sum over. And sometimes in some older textbooks you might see it written as TE, or some more elementary textbooks you might see it written as TE. I think that's bad form. I don't like the idea of two different symbols together with nothing being a subscript or anything like that, because that seems to imply that you're multiplying things together. So anyway, I usually use either capital E or sum over E. Now, some other givens. At the bottom, we're going to call the height 0. That just makes things a lot more convenient. That means that what we actually calculate for the height at the top actually is the maximum height above the bottom of the hill. So, setting it up. We're identifying it's a perfect world problem. We're going to write down our givens, and then we do the total energy equation. Now, the real total energy equation says the total initial energy plus work equals total final energy. But remember, this is a perfect world problem. All of the problems in this video will be perfect world problems, so the work is 0, so we can get rid of that. What does that mean? Well, the work is gone, so next we're going to elaborate on what this sum of energies means. Well, at the bottom we have two types of energy. We have kinetic energy and we have gravitational potential energy. At the top, we have two types of energy. We have kinetic energy and we have gravitational potential energy. In other words, these are the types of energies that are in the problem. So we have them at top and bottom, even if some of them are 0. Then we cross out the ones that are 0. So we're going to get rid of the potential energy at the bottom. Also, I'm going to abbreviate my subscripts now because it's pretty obvious that B is bottom and T is top. This U sub G, we probably don't even need the G subscript here because there's only gravitational potential energy. There aren't any other types of potential energy here. So we could just call it U, capital U, with the appropriate subscript for either B or T, depending on whether it's at the bottom or the top. Now remember, is it moving at the location? If it's not, that means that there's no kinetic energy, and you can cross it out. Does it have height at a certain location? If it doesn't, that means it has no gravitational potential energy, and you can cross it out. So we eliminate the gravitational potential energy at the bottom where the height is 0. we eliminate the kinetic energy at the top, where it's not moving. Well, that simplifies the math. So now all we need to do is we need to plug in for each of our expressions. On the left side, we still have kinetic energy at the bottom. Well, we know our equation for kinetic energy is 1/2 mv squared. So, using a bottom subscript, we have 1/2 mv bottom squared. On the right side, we still need to plug in for that u sub g, the potential energy at the top. Well, potential energy equation is mgh, so potential energy at the top is going to be mg times h at the top, h sub t. Now, it turns out they didn't even need to tell us the mass of the biker. In fact, I was a bad physics student here. I didn't explicitly write my givens, so you can dock me a point or two. But even if I had, I would not have written my mass in this case because I know that it would cancel. I've done so many of these problems before. I knew that my mass would cancel because if I divide both sides by mass, it disappears. So we're asking for the maximum height, so we solve for h sub t by dividing both sides by little g. And now we're ready to plug in our givens, which, again, we were bad physics students and we forgot to write. But anyway, the v at the bottom is 10 meters per second, and that's all we need to plug in. In this case, we get a maximum height of 5.1 meters. So again, we write our givens. HB equals 0, VT equals 0, HT equals question mark, VB is 10 meters per second, M is 80 kilograms, and we say, hey, we're going to use conservation of energy to solve this. Sum of E initial equals sum of E final. And we didn't have a plus W because work is 0. And then it's like, okay, what is sum of E? Well, depending on the subscript, using respective subscripts, each E is a K plus a U. And each K is a 1/2 mv squared, again with appropriate subscripts. Each U is an mgh, etc. And then we go through the algebra, and once we get our expression in terms of the givens, we plug in our givens and the constant of 9.8 meters per square second for G, and we get the answer. Now, what if the shape of the hill changed? Turns out it wouldn't matter, because this is a perfect world problem. In a perfect world problem, there's no friction. When there's no friction, the length of the ride doesn't matter, so the shape of the hill doesn't matter. The maximum height, no matter what, is going to be 5.1 meters, no matter what the shape of the hill is. Depending on the shape, the rider might reach that maximum height at different times, but it will still be at 5.1 meters above the starting elevation. Now, how about this situation? What's the maximum height to which this jet will coast? Well, let's see. The problem tells us that our initial velocity is 250 meters per second, and we're saying, okay, maximum height, the velocity is 0. We'll call the initial height 0 and the final height h final. So we have our givens, and then conservation of energy equation. In this case, I was kind of a little sloppy. I didn't include the sums in front of my energies, but that's okay. Even without the sums, it kind of implies sums. So our conservation of energy statement, total energy initial is total energy final. Well, what are those energies? Well, there's kinetic and potential, and the potential is gravitational potential in each case. So, well, let's see now. At the bottom, we're calling the height 0, so we can eliminate u sub I. At the top, it's not moving, so we can eliminate the final kinetic energy. So what we have left, we plug in for each expression. 1/2 mv squared for kinetic, mgh for potential. And again, use the appropriate subscripts. Without subscripts, it's wrong. Divide both sides by mass, causing the mass to cancel. And then we're solving for the final height, so divide both sides by little g, and now we're ready to plug in our numbers. And we get a maximum height of 3,200 meters above where the engine's flamed out. So plug in our givens with units and get our answer with units rounded. Now, what about making it a little bit harder? What is the speed at a height of 3 meters above the ground? Well, we have the same initial velocity as before, so we know that the bicycle does get to a height of 5.1 meters, if you remember that problem. But that means it went past 3 meters. Well, how fast was it going when it went past 3 meters? We can make a prediction of that. So follow the same steps that we had from before. Write our givens. In this case, I even wrote my mass. Our final height is 3 meters, and we're wondering what V final is. So V final is question mark. So we have our conservation of energy statement, and then kinetic and potential energies. So same first steps as before, but this time the final kinetic energy isn't 0. We know that because we're being asked what the speed is there. So we presume that it's not 0. Well, who knows? Maybe it does turn out to be 0, but we can't assume that from the beginning. So we have to leave it in there. But we did eliminate the initial potential energy because the initial height was 0. So there's where we're at so far. Now we plug in our equations. 1/2 mv initial squared for k initial, 1/2 mv final squared for k final, and an mgh final for u final. Again, if we divide both sides by mass, the masses will cancel. It's always legal to divide both sides by mass. It's just that it won't always cancel. I mean, you can have another expression in here that doesn't have a mass in it, and then dividing both sides by mass might or might not help you, but it won't cancel it completely. We'll get to that later. But in this case, dividing both sides by mass helps. I'm looking for the final velocity, so that's embedded in this 1/2 vf squared term. So I need to subtract a GHF from both sides first, and then I need to multiply both sides by 2. Remember, if you're multiplying both sides by 2, you need to completely multiply both sides by 2. So not only will that cancel this factor of 1/2 on the other side, it'll also give us a factor of 2 in front of the GH. So there we go. And now we take the square root of both sides to get our final expression. And now we're ready to plug in our numbers, which will make sense because notice this minus sign and everything after it is positive. That means that the final speed is less than the initial speed. Well, I would hope so. It's going up a hill. Okay, well, that's good. It agrees with our common sense. These are good reality checks to make along the way. So upon plugging in our numbers, we get a final speed of 6.42 meters per second. How about this situation? How fast is this bungee jumper going after falling a distance of 50 meters, assuming that the bungee cable hasn't begun to become taut until 50 meters? So how fast is the bungee jumper traveling at that point? Well, set up our conservation of energy statement and work it out. So we have our givens. In this case, we're saying the velocity at the top is 0. I'm calling the height at the top 50 meters and the bottom height 0. I could have done it differently. I could have called the top 0, but then I would have needed to call the bottom negative 50 meters. And since I'm allergic to negative signs, I decided not to do that. So, conservation of energy. Total energy at the top equals total energy at the bottom, which means kinetic at the top plus potential at the top equals kinetic at the bottom plus potential at the bottom, because we have kinetic and gravitational potential energies relevant in this problem. Well, it wasn't moving at the top, and we're calling the bottom height 0, so we're able to eliminate a couple terms. And then we plug in mgh for our initial potential energy, and 1/2 mv squared for our final kinetic energy. And again, dividing both sides by mass cancels the masses, and we're solving for the speed at the bottom, so we're going to multiply both sides by 2, and then we're going to take a square root. So v bottom is square root of 2gh top. And now we're ready to plug in our givens, with our h top being 50 meters. So let's take an opportunity to do a little bit of mental math here. So I wouldn't do a 2 times a 9.8, that's 19.6, but that's harder. I want to do a 2 times a 50, that's 100, that's easy. I can multiply lots of things by 100, just add 2 zeros, or shift the decimal place over by 2. Well, 100 times 9.8 is going to turn into 980. What's the square root of 980? Well, I know that 3 squared is 9, which means that 30 squared is 900. So the square root of 900 is 30. I mean, also just square root of 900, well, that's square root of 9 times 100, which means 3 times 10, which is 30. Well, this is over 900, it's 980. So I expect my answer to be a little bit over 30. It's going to be 30-something. In fact, it's going to be 31 point something. So 31.3 meters per second, as it turns out. So the mental reality check worked out. Mental reality checks are very good things to do because fat finger errors on calculators are very common. Let's look at another kind of problem. So if an upright vertical spring with a force constant of 860 newtons per meter is loaded with a large clock and pressed down 2.5 meters from equilibrium, calculate first the elastic potential energy, and then B, the velocity of the clock when it's 6.5 meters above equilibrium, and then C, the maximum height of the clock above its initially compressed position. All right, so first, calculate the elastic potential energy. We're going to write our givens. Remember the equation for elastic potential energy, that is spring potential energy, U sub S, is 1/2 kx squared. So don't forget that. That's something that should be memorized. And now we plug in our givens. So U sub S, plug in our K, plug in our X initial, and work everything out, and we get 2,690 joules. Okay, great. So now we know the initial elastic potential energy. Well, how high does it go? Or sorry, what's its velocity? 6.5 meters above the starting position. So we set up conservation of energy. So we have our givens. Again, no work is done here. So we just have total energy initial equals total energy final, since W is 0, so no plus W on the left. Well, notice we have multiple types of potential energy here. So the subscripts are very important. So we have K initial plus U sub G initial plus U sub S initial, where U sub S is elastic potential energy, spring potential energy that is. U sub G is gravitational potential energy. And we have the same stuff final. Now, looking back at my givens, I see a lot of zeros there. X final is 0. In other words, the spring is not compressed at the end, so I can get rid of elastic potential energy at the end. H initial is 0, so I can get rid of initial gravitational potential energy. V initial is 0, so I can get rid of initial kinetic energy. So lots of things are 0. What's left is the initial elastic potential energy, the final kinetic energy, and the final potential energy due to gravity. And we're asked to find the velocity at that height of 6.5 meters. So now you might be tempted to divide both sides by mass, and that actually is one of the things we're going to need to do in order to solve for our final velocity. But notice that when you do that, it will not completely cancel. It'll go away from the mgh term, but you're going to have a mass in the denominator of the 1/2 kx squared term. Okay, so first, since we're interested in the final velocity that's in this term right here, we subtracted an mgh final from both sides, and now we're going to get rid of the stuff that's multiplying and dividing our final velocity. So we're going to multiply both sides by 2 and divide both sides by m. So this is the result of doing that. Multiplied both sides by 2. That got rid of this half here and gave us a 2 there. Divide both sides by m. That got rid of the mass right here and gave us an m in the denominator right here. So notice the masses again did not completely cancel. Now we take the square root of both sides. Yay, there's our final expression. All right, so we're ready to plug in our givens. So here we go, plugging in our givens and working out the math. We realize, we have a negative number under the radical, and only Chuck Norris can take the square root of a negative number. So we seem to have an imaginary velocity. What went wrong? Apparently, what went wrong was our assumption. Just looking back here, this mgh term was too big. Or at least the result of the mgh term was too big after canceling things and stuff like that. How could it be too big? Well, g is g. So apparently the height was too big. Our assumption that the clock that it ever reached a height of 6.5 meters was wrong. Oh well, too bad, so sad. So the clock never gets to a height of 6.5 meters. There was not enough elastic potential energy to reach that height. Well, what was the actual maximum height? Well, in the first part of the problem, we already calculated the initial potential energy, which was all elastic, 2,690 joules thereabouts. Well, that's going to be, remember, total energy is conserved. So that's going to be the total energy at the maximum height as well. So we also know that at the maximum height, it's all potential energy. So I just set that number equal to mgh. And it's all potential energy because we're assuming it doesn't have any horizontal speed or anything like that. So in any case, I set that equal to mgh final and solved for h final. Divided both sides by mg, plugged into my numbers, and got a final maximum height of 5.27 meters. So we've gone through a number of conservation of energy problems. We went through problems where we only had initial kinetic energy and final potential energy due to gravity. We went through problems where we had a problem where we had kinetic energy at the beginning and at the end. We had a problem where we had all potential energy at the beginning and all kinetic energy at the end. And then finally we ended with a problem with multiple types of potential energy. So this really does it for all of the types of conservation of energy problems that we're going to be solving in this unit, where energy actually is conserved in a closed system. In the next video, we're going to look at problems to see how we will deal with situations where there is work being done, where there are external forces or energy is being lost, things like friction, rockets, etc. So, hope to see you then, and thank you for watching.